All right, so now that you've seen that demonstration, let's take a look at the math that is going with that. So we started out with just an object on an inclined plane. Let's take a look at the free body diagram here, start drawing in those forces. We know always force due to gravity acting straight down. So force due to gravity, which remember is equal to mg. Okay, what else do we know is acting on here? Well, if we've got a weight, there's going to be a normal force from that surface, unless we're straight up and down, in which case there's nothing under here to support the object anyway. If there's a surface and the object is touching that surface, and some amount of that surface is helping to support the object, there's got to be normal force. And remember, normal force has to be perpendicular to the surface. Has to be perpendicular to the surface. That's what it means, normal meaning perpendicular. Okay? In this example, we're talking about friction, so there also has to be some force of friction. Okay. Now, we also have the fact that the force of the weight is actually divided into two component forces in the x and y direction. This is really, really key for these inclined plane problems, that the weight is what's being divided up. When we were talking before about a force being applied at an angle, it was that applied force that was being broken up. But it's different when we have an object on an inclined plane. For that situation, it's the weight that's being broken up, because we're changing the surface. The surface is what's different. When we were doing this problem, the applied force was what was different. It was being applied at an angle, but here, weight is being applied at an angle. And the only reason that I'm saying that weight is being applied at an angle as opposed to the rest of these is because it's easier to just break up one vector instead of the other three. So let's talk now about identifying all of these different forces and how we actually go about calculating them. So I'm going to actually just list all of the different equations for these forces, including the force due to gravity in the in the y direction, which is this component here vertically, and also the force due to gravity in the x direction, this parallel force, parallel to the surface, perpendicular to the surface. Okay. We know that the force due to gravity in the x direction specifically, really, it's more important for us to think about x and y independently, because we always look at the forces on an object in the x direction and then in the y direction separately. When they're perpendicular to each other, they don't affect each other. I can stand on a table all I want and push down as hard as I can. Any force that's acting perpendicular to that surface is not going to cause it to slide around. And I can push horizontally on an object as hard as I can, and that's not going to affect the forces up and down. So when forces are perpendicular to each other, they don't affect each other at all, because they don't interact. Okay, so we've got Fg, specifically, let's start out with specifically in the x direction. Fg specifically in the x direction. So this component right here that is acting parallel to the surface. And that is, we know mg, we know that we solve this side of the triangle by taking sine of theta times the hypotenuse. And all I'm doing there is remember that sine of theta is equal to opposite over hypotenuse. Well, FGX is the opposite. FG is this hypotenuse here. So sine of theta, remember theta and theta, those are congruent. Sine of theta is opposite over hypotenuse. So if I want then to find the opposite, which is my FGX, sine of theta times hypotenuse. So that's the step that I'm doing to get this. FGX is mg, the hypotenuse, times sine of theta. Times sine of theta. That's the equation for it. Okay, then we've got FG of y, so the other one. Well, if I'm solving for the adjacent side of the triangle, I'm just going to do the same procedure except use cosine instead of sine. So that's going to be mg times cosine of theta. Good so far? Okay, now the question is, how am I going to figure out these other two forces, normal force and force of friction? What we have to be able to do is look at the specifics of the problem. Is the object accelerating? Is the object at rest? Is the object moving with a constant velocity? So we're going to think of this problem in terms of the problems that are in your practice, where the object is either at rest, so not moving at all, or moving with a constant velocity, or just beginning to move with a constant velocity. And so that's going to tell me that we're in equilibrium. Well, if we're in equilibrium, then that tells me that the sum of my forces acting in the x direction have to be equal to 0 newtons. They have to be balanced. So the ones that are acting down and up have to be balanced. Same size, opposite direction. Same goes for the forces in my y direction. So this force down in my y direction has to be equal and opposite to the force going up. So basically, we already got those equations. We're good to go. So so that means normal force is equal to Fg in the y direction. These have to be equal and opposite if we're in equilibrium. So Fn is equal to Fgy, which is mg times cosine theta. Now, granted, Fgy is going down, so it's negative, and Fn is going up, so it's positive, but they're the same size, same magnitude, opposite directions. So opposite signs, positive and negative. So these two are they're pairs. They're balanced. They're in equilibrium. Now then, force of friction, whether it's static friction or kinetic friction, that force of friction is equal to, it has to be equal to this component here that's acting parallel to the surface. So this component right here, this Fg in the x direction, this component that's acting parallel to the surface is the force that's pulling down. If this object is either at rest on the surface or it is moving with a constant velocity, then these forces are balanced and they're going to be equal to each other, which means that these are buddies. So force of friction is going to be Fg of x, same size, just opposite directions, one up and one down. And that's going to be mg times sine of theta. Okay. Now the overall goal here is in these specific problems 4, 5, and 6, talk about finding either an angle or a coefficient of friction. And the only information you're getting is either the angle to solve for coefficient of friction or coefficient of friction to solve for an angle. You're not given mg. Or, well, you're at least not given m, because we know that g is 9.8 every time. Remember? So we have to figure out some other relationship. We have to figure out now some other relationship for the weight. And so that means, I'm sorry, not for the weight, some other relationship for the friction. Well, there is another equation for friction, and that is this. Force of friction is equal to normal force times coefficient of friction. Right now, regardless of whether it's static or kinetic, that's not the point. Friction is normal force times mu. Do we have an equation for normal force? Yes, we do. It is this one. There's beginning to be a relationship that we can see here. Is there a relationship between this and this maybe? Things that are going to cancel out if we put them together. What we can say then is if force of friction is normal force times mu, well then we can say that force of friction, which we've already defined as mg times sine of theta, because this force of friction has to balance this, well that's also equal to normal force, which is mg times cosine of theta times my coefficient of friction. Now I've got some things that I can cancel out. If I only know mu, for example, 0.25, let's say. I think that's one of the examples on here. Or maybe that was your quiz. I'm starting to forget. And I need to find the angle. Well, the relationship then between these, we can actually start canceling some things out of this relationship. First thing that you might notice that's the same is mg. Well, I can divide both sides by mg, cancel that out on both sides. And so then I've got sine of theta on one side being equal to the cosine of theta times mu. Anything else I can do with that? Another step? If we divide both sides by cosine, then sine divided by cosine is tangent, right? Well, then that means that mu is tangent of theta. What do you think? So, when we're looking at those problems, 4, 5, and 6, they're only giving you one piece of information, either coefficient of friction or angle of inclination. And I think 4 actually also tells you a mass, but what happened to mass in this problem? Got canceled out. Wasn't even necessary to begin with. So that's actually extra information. So when we have these questions, the equation that you need is tangent of theta. It is important for you to be able to understand why that is an okay equation to use, where it comes from in the first place. This is where it comes from. If you're still struggling with it, let me know, because it does matter that you understand the physics behind why this is okay to do. Okay.